Welcome back. So, in the last lecture I introduced the concept of continuous time, continuous variable pricing of the option, which is known by the Black-Scholes model. This is the fundamental model of option pricing in the continuous time framework. In the discrete time we had the binomial model, and in the continuous time we have the Black-Scholes model as the equivalent of the binomial model. The time progression is continuous in this case, whereas the spectrum of stock values that can be modeled are also continuous. But there are certain assumptions which I discussed yesterday. So, a quick review of the assumptions: the stock price follows the log normal process in finite time, and it follows the Ito equation or the Langevin equations in the infinite simul time. We shall come back to it. Short selling of securities is fully allowed with no restriction on the utilization of the proceeds that are arising out of short selling of the securities. There are no transaction costs, no market frictions. No dividends during the life of the derivative from the underlying asset, no income arising from the underlying asset during the life of the derivative. No riskless arbitrage opportunities. In other words, we are living in a efficient market where arbitrage is not allowed. Where arbitrage will where arbitrage will ensure that the prices conform to the same risk level in the event of there will be no differential pricing of assets having the same risk profile. That is what is meant by no riskless arbitrage opportunities. If there is a differential pricing in respect of the same risk same risky assets or same level of risk of assets, then that will be arbitraged away. Security trading is continuous, that is an approximation, and the risk free interest rate is R, again assumed constant over the maturities. In other words, we are assuming that the term structure of interest rates is flat. So, then we started the derivation of the Black-Scholes model in the last lecture. We started with the Ito equation or the Langevin equation representing the stock price process. ds is equal to mu s dt plus sigma s dw. dw is the standard Brownian motion. This of course is equivalent, as we have seen earlier, to the log normal stock price process over finite times. Then the other input that we had was Ito's lemma. Ito's lemma is in respect of a function of the stochastic variable of a given stochastic variable x, where the stochastic variable x follows the stochastic differential equation dx is equal to a dt plus b dw, and g is of course continuous and at least twice differentiable, it could be more. Then using Ito's lemma we get the differential of g in this expression, and as I mentioned this expression is additional to what we have in conventional differentiation, and this arises because the expected value of dw square is equal to dt and is non-stochastic and has to be taken into consideration, it cannot be ignored. You can also say that the variance of dw is dt, which also and is non-stochastic, therefore, dw square term cannot be ignored in the Taylor expansion. Then making the various substitutions, we got the differential for the derivative price. We are representing it by c. We got the differential for the derivative price as this expression by using the Ito's lemma, substituting c s t for g x t, substituting ds equal to mu ds dt plus sigma s t w for dx. So, a becomes equal to mu s and b becomes equal to sigma s. Making these substitutions in the Ito equation, we get this particular equation 3. We now move to the fundamental assumption that I mentioned when I started talking about option pricing, that the premise or the philosophy of option pricing or the pricing of a derivative is that we can construct a risk free asset comprising of opposite positions in the derivative and in the underlying asset, and therefore, the derivative can be assumed to comprise of a certain position in the underlying asset and the risk free asset. We do precisely the same thing. We constructed a portfolio comprising of one unit of the derivative it could be a long position and a short position. The important thing is that these two positions should be opposite, but let us assume that the derivative is long and the underlying asset this del C by del S units of stock. These two things are combined to form a portfolio. Let us call that portfolio capital pi. So, the value of capital pi at the point of construction is equal to C, which is the price of one derivative security, minus, because it is an opposite position. So, if we are short selling this stock, you will get the money, it will be an inflow if the cost of derivative is an outflow. So, del C by del S into S, where S is the stock price, del C is the del S by is the number of units of the stock into S, which is the stock price. So, this is the price of creating the stock position, this is the price of creating the derivative position, because the positions are opposite, there is a negative sign. So, this is the value of the riskless portfolio. Why it is riskless? We are coming to that. The change in the value of pi, change in the value of pi over a small interval of time dt, in which the stock price changes by ds, is given by d pi is equal to d c minus del C by del S into ds. Now, the important thing here is that we are assuming that del C by del S remains constant over this interval of time, which we are considering in this particular case. This interval is so small that the slope del C by del S is constant over this particular period of time. Now, the next step is that we, for the moment, let us assume that this portfolio pi is riskless, and because this portfolio pi is riskless, over this interval of time dt, it will generate the risk free rate of return, and therefore, what does it mean? It means d pi will be equal to r into pi into dt, or looking at it at the other way around, and d pi upon pi, that is the percentage change in the value of the portfolio, and normalized by dt, that is 1 upon dt, that is per unit time, that is the percentage change in the value of the portfolio per unit time will be the risk free rate. So, that is precisely what this equation represents. Now, coming back to the point that this particular portfolio that we have constructed is risk free. Let us look at this. We have d pi is equal to, we just recap here, d pi is equal to d c minus del C by del S into ds. We shall be using this particular equation. Now, d c we have expanded in terms of the Ito equation, we have done it earlier, we are simply reproducing the result. So, this is this particular portion from here to here represents the value of d c, is nothing but the Ito equation, minus del C by del S as it is into ds. Now, what is ds? ds is this expression. This was the fundamental assumption we made about the stock price process. Now, if you look at this very carefully, you immediately find that this term cancels out with this term, del C by del S into sigma S del dw, del C by del S sigma S dw. So, these two terms immediately cancel. Of course, there is another cancellation, the other cancellation is this one, but we are more concerned with this dw cancellation. Why we are more concerned with this dw cancellation is that this dw is the component which represents the volatility. You see, the unpredictability or the stochasticity, the randomness in this particular set of equations arises from dw. In the call process, call price process, as well in the stock as in the stock price process, the randomness arises from the dw, and we are observing from this that the change in the portfolio value that we have constructed, that portfolio that we have constructed of the derivative and del C by del S units of the stock is such, that portfolio is such that the portfolio price process or the return on the portfolio, the change in value of the portfolio becomes independent of dw. In other words, it is a deterministic evolution now, it is not a random evolution. The randomness in the call price process, which is represented by this portion, is annulled by the randomness in the stock price process, which is represented by this equation. That was the fundamental assumption that we started with, and that is very well exposed in this particular equation. So, secondly, this mu s and mu s also get cancelled out, and we are left with this particular value for the change in the value of the portfolio over a time dt. Again I reiterate, the important assumption is that del c by del s remains constant over time dt, right. So, because this is independent of the this does not have any volatility term, it is independent of fluctuations, it is independent of randomness, therefore, it will generate the risk free rate, and which gives us this particular equation. Let us continue. Now, what do we have? D pi is equal to r into pi dt, but what is pi? Pi is c minus del c by del s into ds. Okay. So, d pi is equal to d c minus del c by del s into ds, this is the left hand side, and on the right hand side I substitute the value of pi as c minus del c by del s into s. This is the value of capital pi, this is the cost of setting up of the portfolio, and this is the change in the value of the portfolio over a small time interval dt when the stock price changes by ds. So, we have simply substituted the value of pi here, we have done nothing else, and now we get two expressions for dc. The first expression that we get is from this this particular equation, we move this to the right hand side, and we get dc is equal to del c by del s into ds plus r c dt, this particular term, minus r del c by del s s dt, r del c by del s s dt. This is this term, this is this term, and this is this term moved to the right hand side. So, dc is equal to this expression. ds can be written in this form. We started with this assumption, that was the stock price process model. So, we simply substitute ds is equal to this expression, and the rest we retain as it is. Now, as far as dc is concerned, we also have another expression for dc from the Ito equation that we have talked about just now, and dc is equal to this whole thing coming from the Ito equation, substituting g is equal to c and substituting a equal to mu s and b equal to sigma s, we get this expression. We equate the two values of dc, this is the expression A for dc, this is the expression B for dc. If we equate these two expressions, this mu s goes, this sigma dw goes with this sigma dw. So, this whole expression goes, and if you bring everything to one side, the rest of the things to one side, dc by dt is this expression, this is this expression, this has been cancelled out. This R c is here, when you bring it to the right hand side, it will be minus R c, and this minus R s, when we bring it to the right hand side, will become plus R s. The whole thing will be multiplied by dt, and because dt cannot be 0, this whole expression must be 0, and this is the Black-Scholes equation. Black-Scholes PD partial differential equation for the derivative price. So, this is how we arrive at the Black-Scholes equation for the partial derivative equation for the derivative price. Now, for a call equation, what should we have? The terminal condition, what should be the boundary condition? The terminal payoff from the call option has to be maximum st minus k and 0. So, this must constitute the terminal condition for the call option, and similarly for the put option, because we are talking about European options. Similarly for the put option, the terminal condition will be maximum k minus st 0. So, the previous Black-Scholes partial differential equation needs to be solved with the reference to these terminal boundary conditions. And what is the solution? We shall talk about the solution later, but the result of all the solving of the Black-Scholes equation is written here. C is equal to, C is the call premium of a European call option on a non-dividend paying stock. So, C is equal to S naught phi d 1. What is phi 1? Phi d 1, phi d 1 is the cumulative normal distribution function of d 1 up to d 1, and similarly minus k to the power as the phi of d 2. This is the phi means, I reiterate, is the cumulative normal distribution. So, it covers all values of, in other words, it covers all values of the random variable up to d 1 and up to d2 respectively. d1 and d2 are defined by this slightly complicated expressions, natural log of S0 minus x0 upon k plus r plus 1 by 2 sigma square into t. T is the remaining time to expiration, please note this. Sigma is the volatility, S0 is the current stock price, k is the exercise price, r is the risk free rate. Now, we come to certain results, certain interpretations of the Black-Scholes equation. We have derived the Black-Scholes partial differential equation, we have got the boundary conditions, we know the solution as well, although how the solution has been arrived at we will talk about later, it is an exercise in itself. So, we will talk about it later, but for the moment we now will talk about certain outcomes, certain derivations, certain implications, certain interpretations of the Black-Scholes equations. What is the probability that a call option will be exercised in the Black-Scholes framework? Now, we know that the call option will be exercised if ST is greater than K, because what is the call option? A call option is the right to buy. So, if the market price is higher than the exercise price, I would rather exercise the call option and buy the stock using the exercise price rather than buying it in the market. So, the call option would be exercised if ST is greater than K, and the payoff in fact from the call option is maximum of ST minus K and 0, and obviously this would be positive only when ST is greater than K. Therefore, the option also would logically be exercised only when ST is greater than K. Hence, we need to find the probability of call exercise, we need to find the probability of ST, that is the stock price on maturity of the call, to be greater than the exercise price. We need to find the probability of the stock price being greater than the exercise price. Now, because the log of x is a monotonic function of x, therefore, probability ST greater than K can also be is equal to probability that log ST is greater than log K, because the monotonic relationship between x and log x. But we know that log of ST, is normally, I reiterate, ST is log normally distributed. Therefore, log of ST is normally distributed, and log of ST is normally distributed with the mean of this expression. This is the mean. Remember, we are working in the risk neutral world. So, we will not have mu here, we will have r. R is the risk free rate. Because we are working in the risk neutral world, the return will be risk free, we have talked about it. The return will be risk free and not the actual expected return in the real market, that is not relevant to this, to working in the risk neutral world. Therefore, log of ST is a normal distribution with a mean of this expression and a variance of this sigma square t. So, let us see where it takes us. Now, we want to find probability of ST, log of ST greater than log of K. This is equal to 1 minus probability of log of ST being less than log of K. It is a continuous distribution. So, you can as well put less than equal to here, and that is equal to 1 minus. Now, we are transforming this log of ST is normally distributed, but we are transforming it to the standard normal variate. What is the corresponding standard normal variate? Z. So, what is the relation between Z and X? Z is equal to x minus x bar upon sigma. How do we standardize a normal variate? We standardize a normal variate in this form. Z is the standard normal variate corresponding to a given value of our normal variate x minus x bar is the expected value upon sigma is the standard deviation. So, we are doing precisely the same thing. In our case, x is equal to log k, x bar is equal to this whole expression, the mean value, because a log of ST is distributed normally with this mean, and the standard deviation sigma in our case is sigma root t. So, Z must be equal to log k, that is x, minus x bar, which is this expression within square brackets, divided by sigma, which in our case is sigma root t. So, 1 minus p. Now, what is this expression? This is nothing but the cumulative normal distribution, cumulative normal distribution up to this value. So, this is nothing but cumulative normal distribution up to this whole expression 1 minus cumulative normal. In other words, what are we saying? We are saying this expression from p onwards is the probability that z takes values up to a maximum threshold of this particular expression, which is nothing but the CDF up to this value of x. So, that is phi of this expression, and this one of course remains 1 minus. Now, we have 1 minus n of x is equal to n of minus x, or 1 minus, sorry, since I am using phi here, 1 minus phi of x is equal to phi of minus x. I write it again, 1 minus phi, capital Phi of x is equal to phi of minus x. That is precisely what I am using, 1 minus phi of x is equal to phi of minus x. And this whole expression, if you look at it carefully, is nothing but phi of d2. With d2 defined earlier, where is d2 defined? d2 is defined here, this is d2. If you look at this d2 and if you look at this d2 expression here, you find that it is precisely the same thing, and this is nothing but phi. You see this this minus sign and this minus sign becomes plus. So, we have log of S0 minus log k, which is log S0 upon k. So, this term together gives me log S0 upon k. This minus and this minus give me a plus here, plus r minus 1 by 2 sigma square into t, which is divided by sigma root t, which is nothing but d2. So, this is phi of d2. So, what do we get? We get that the probability of exercise of the option, probability of exercise of the option is phi of d2. Probability of exercise of a call option, rather, probability of exercise of a call option is equal to phi of d2. That is one interesting result. Then we now talk about the delta of a call option. Remember, delta is given by del C upon del S. So, we want to work out the value of del C upon del S. We start with the expression for the Black-Scholes solution. The value of a call is given by S phi d1 minus k e to the power minus r t phi d2. So, del C by del S, when we take the derivative with respect to S, this goes, we are left with this, plus you have we are using the UV rule here. So, this is my u, this is my v, u into derivative of v plus v into derivative of u minus, in this case this whole thing is independent of S. So, it comes as it is, and we have the derivative of d2. Now, we work out these two derivatives, this derivative and this derivative. We have phi dash of d1 is equal to this. Remember, what is phi d1? I had written the value of phi d1 in the first slide. It is the integral, let me write it down again, phi of d1 is equal to 1 upon under root 2 pi into what is it, sigma root sigma square t into sorry, this is 1 upon under root 2 pi integral minus infinity to d1 e to the power minus 1 by 2 d1 square d of d1. This is this is the standard normal variate or the cumulative distribution of the standard normal variate d1. So, phi of d1, the cumulative distribution is given by 1 upon 2 pi sigma root sigma square t will be 1, because the variance of the standard normal variate is 1. So, 1 upon root 2 pi integral minus infinity to d1, and this integration variable should be given a different name actually. It should be, let us say, it should be z or t or whatever into dz. So, I will write it again, phi of d1 is equal to 1 upon under root 2 pi integral minus infinity to d1 e to the power minus 1 by 2 z square dz. And this is what phi d1 works out to. So, when I take the derivative, why this is differentiated with respect to d1, this integral will go, I will get this expression, and then the d1 has to be differentiated with respect to x. Now, when you differentiate d1 with respect to x, you get 1 upon sigma s root t. As you can see here, this is my d1. So, differentiating it with respect to x, I get log of derivative of log x, which is 1 by x into sigma root t as it is. This is independent of s, and this expression is entirely independent of s. So, this contributes nothing to the derivative. Derivative is 1 upon s into sigma root t, right. So, combining the two expressions, I get phi dash d1 is equal to 1 upon sigma s root t into 1 upon root 2 pi e to the power minus 1 by 2 d1 square. Taking s to the left hand side, I get this expression. Similarly, working on similar lines, I get for phi dash d2 1 upon sigma s root t 1 upon root 2 pi e to the power this parallel derivation and nothing different absolutely. Multiplying both sides by k e to the power minus r t, I get this expression. Now, I deduct the second from the first. So, what do I get? I get s phi dash d1 minus k e to the power minus r t phi dash d2 is equal to, I take this expression outside the bracket, I have 1 upon root 2 pi also I can take outside. Within the bracket I have e to the power minus 1 by 2 d1, which comes from here, and k e to the power minus r t upon s, since I have this s is here. So, this is this s, right. So, k e to the power minus r t divided by s e to the power this expression. Now, this expression is 0. This expression I can put it together with this, k upon s can be written as e to the power log k upon s. So, I have written it as e to the power log k upon s. E to the power minus r t is already in exponential form, this is also in exponential form. So, simply writing k upon s as e to the power log k upon s, I can write this expression in this form. Now, this expression, this whole expression is 0. Why? That is given in the next slide, but this expression becomes 0. So, this whole expression becomes 0, and therefore, the net result that we have is that the delta value that we are looking for, del c by del s, becomes equal to phi of d1. That is the only term that remains from the differentiation. When you do the differentiation, these two terms cancel each other and we are left with simply the first term, and therefore, delta equal to del c by del s is equal to phi of d1. Right. Now, I prove that what do I prove? I prove that this whole expression is 0. This whole expression will be 0 if this expression is equal to minus 1 by 2 d1 square. That is what I am going to prove. Log k upon s minus r t minus 1 by 2 d1 square is equal to this. That is what I have to establish. So, now d2 is equal to d1 minus sigma root t. So, I write d2 as d1 minus sigma root t square whole square. Now, I do the squaring. When I do the squaring, I get this one as it is, I get this one as it is, I get 1 by 2 d1 square minus 1 by 2 this expression sigma square t by a square plus b square minus 2 a b. This 2 will cancel with this 2, and I will have d1 sigma root t, d1 sigma root t. Leaving alone the minus sign, I have log s upon k plus r plus 1 by 2 sigma square into t, which is nothing but sigma root t into d1, sigma root t into d1. This minus sign comes here. So, I have sigma root t into d1 minus plus this thing plus sigma d1 sigma root t. So, this expression and this expression cancel each other, and I am left with minus 1 by 2 d1 square, which is here. So, this whole expression gives me minus d1 square, which was to be established. Thank you. We will continue after the break.